In this video, I want to talk about how we measure resistance, or more specifically, I want to talk about the Wheatstone bridge. So the Wheatstone bridge circuit is used to precisely measure resistances of usually medium values, so something in the range of 1 ohms to 1 mega ohms. So let's just quickly go over the components of a Wheatstone bridge. So the bridge circuit consists of 4 resistors. So we have R1, R2, R3, and Rx is the unknown resistor that we want to measure. In addition to these 4 resistors, we have this DC or direct current voltage source. So this is equivalent to a voltage source that we usually show it like this. So these two are practically equivalent. In addition, we have this detector here that connects this node and this node together. So as I said, R1, R2, and R3 are known resistors. So we know the value for these resistors, while Rx is the resistor that we want to find its value. So R3 is usually a variable resistor, like a potentiometer. So basically it has a small screw on top of it, and by rotating the screw, we practically change the value of R3. What about the detector? So the detector is usually a Darson voltmeter, which can be very precise, especially in the micro ampere range. And this type of detector is usually called a galvanometer. So let's just quickly go over all the components. We have R1, R2, and R3. We know the values for R1 and R2, and also we know the range of the values for R3. What we don't know is Rx. We have this DC or direct current voltage source that basically powers up the whole circuit. And then we have this detector connected between these two nodes that is measuring the current that goes through this wire. So to measure the value for Rx, we change the variable resistor R3 until there is no current shown by this galvanometer. So until the current that goes through this line is 0. If that happens, the value for Rx equals R2 over R1 multiplied by R3. So this is the simple equation that we have for the Wheatstone bridge. But now the question becomes, how did we get to this conclusion? So let's just go over the condition for which this equation is satisfied. So we said that we change the value for R3 until the current that goes here is 0. So let's just quickly draw some current directions. So I assume the direction of the currents to be like this. So we have I1, I2, and then we have I3 and I4. And for the galvanometer, I use IG in this direction. So let's just write down the KCL for node A, and then we do it for node B. So let's just see what we get. So KCL for node A means that negative I1 plus IG plus I3 equals 0. So since IG is 0, so we are writing it when IG is 0. This means that I1 would be equal to I3. Let's just do the same for node B. So for node B, we have negative I2, negative IG plus I4, let's just call it IX. So IX equals 0. Since IG equals 0, we have I2 to be equal to IX. So these are the two equations that we get when IG equals 0. So that is the condition for these two equations. And again, we change R3 until we get IG to be 0. So what else we can get when we have IG to be equal 0? So let's just say this voltmeter has a very, very tiny internal resistance. So let's just call it RG. So even though this RG might not be completely 0, but at the time when IG equals 0, that means that there is no voltage drop across this resistor. So VG, for when IG equals 0, VG, which is equals to IG multiplied by this tiny RG, equals 0. So in this case, node A and node B are practically at the same voltage. So you can think of them as being connected to the same point. So when this happens, based on KVL, we can conclude that R1 multiplied by I1, you see, this point, let's just call it C. So we said that based on this conclusion, we can say A and B are both at the same voltages, right? So that means that the voltage between C and A is equal to the voltage between C and B. What is the voltage between C and A? Is R1 multiplied by I1. What is the voltage between C and B? It's R2 multiplied by I2. So it is R2 multiplied by I2. The same can be said between point A and D and also point B and D. So we have R3 multiplied by I3 equals Rx multiplied by Ix. So these are the two additional equations that we have. So now what we are looking for is Rx. So based on this equation, Rx equals R3 I3 divided by Ix. Right? So based on the above equation, we know that Ix equals I2. So I just write it as R3 I3 divided by I2. So what is I2 here? I2 from this equation equals I2 equals R1 divided by R2 multiplied by I1. And also from the top equation we know that I1 equals I3. So this is R1 over R2 multiplied by I3. So now let's just replace I2 in this equation and see what we get. So we have R3 multiplied by I3 divided by R1 over R2 multiplied by I3. So now we have I3 on the numerator, we have I3 on the denominator. So this becomes R3 divided by R1 over R2. So if I rearrange this, I get R2 over R1 multiplied by I3. So the final equation is basically what we have here. So Rx, when R3 is changed to the point where Ig equals 0, equals R2 over R1 multiplied by R3. So that is equivalent of saying that R1 Rx equals R2 R3. So the multiplication of R1 and Rx equals the multiplication of R2 and R3. So that is another conclusion based on these assumptions that we have. So if we have the value for R1, R2, and R3, we can find the value for Rx. So again, when the bridge is balanced, basically when Ig is 0, Kirchhoff's current law requires that I1 be equal to I3, I2 be equal to Ix. Also, because Ig is 0, there is no voltage drop across the detector, right? Because even if this one has a small Rg, when it's multiplied by a 0 value to calculate the voltage drop, it's going to be 0, which means that I3 R3, so the voltage here, equals Ix Rx, and also I1 R1 equals R2 I2. And now, based on the calculation on the previous slide, we can combine them. We get to this conclusion that Rx equals R2 over R1 multiplied by R3, or R1 Rx equals R2 R3. Basically, the multiplication of the resistors on the diagonal directions are equal. So R1 multiplied by Rx equals R3 multiplied by R2. So there are some things that you need to be considering when designing a Wheatstone bridge. So the first thing is that if the ratio R2 over R1 is unity or 1, then Rx equals to R3. So in that case, R3 must vary over a range that includes the value of Rx, right? Remember, this one was a variable resistor. So if the range over which R3 is changing does not include Rx, when R2 over R1 equals 1, then you cannot find the value for Rx. The other thing is that to cover a wide range of resistors, we must be able to vary the ratio R2 over R1, which requires accurate and decimal values like 1, 10, 100, and 1000 ohms for R1 and R2. So we use these very accurate resistors to switch R1 and R2 to be able to go over or like cover a wider range of resistors. The other thing that you should note is that lower resistances are usually difficult to measure because of the thermoelectric voltage generated in the junction of the dissimilar metals and because of the thermal heating effect. So practically, if you want to measure a very small resistance in this circuit, because of all the simplifications that we made to create this mathematical model, to create the electric circuit, the value that you get for Rx is not going to be very accurate, right? Because, for example, we say Ig is 0, right? But in practice, it's not usually exactly 0. It is a little bit off, right? Because of all the other physics that we didn't take into account. So usually this technique is not a very good technique to measure small resistances. On the other hand, higher resistances are difficult to measure too because of the leakage current that can be comparable to the current in the branches of the bridge circuits. So that's why when I first introduced the Wheatstone bridge, I said that it is a good approach to measure resistances in a medium range. So somewhere between 1 ohm to 1 mega ohm. So if the resistor that we want to measure is less than 1 ohm or it's greater than 1 mega ohm, you should think of other ways to do the measurement. So in this video, we learn how to measure the resistors in general, and we introduced the concept and the circuit of Wheatstone bridge, which is a common way for us to measure resistors that we don't know their exact value.